Welcome, everyone. This is Data Science DC. We are doing a hybrid meetup. Everyone hear me okay? I have people in front of me who are like, yeah, I can hear you. And then there's people online. So if you're online and having issues, let me know. I think I'm hearing some reverberation. Yeah, one second. Be great. Awesome. Well, today we're going to be talking with Roni Kobrosly about causal thinking in data science. And right before we get started, I just want to give a shout out that we have a good number of meetups here in the DC area. More of them are starting to get back online in person. So I encourage you to go to datacommunitydc.org and check those out. Data Community DC is the parent nonprofit that all of these meetups fall under. And we have a new one too, actually, R-Govies, for R and government. That's where that comes from there. Is new to the fold and going to be getting started here too. So excited to welcome them. But go to Data Community DC and get all the details. I want to say thank you to our sponsors, Prefect, who's also my employer. So thank you, Prefect. ATA, also a good sponsor for us, and Red Hat. We are at Red Hat's offices right now in McLean, broadcasting to you all, and want to give a big shout out to Red Hat. So Janet and Tommy and myself are the organizers of Data Science DC. If you have questions, want to get in touch with us, this is how you do it. Those are Twitter handles down there at the bottom. Feel free to tweet out about the event today too. We do have a code of conduct. Yes. Yep. Oh.
It may be a second desktop.
Oh. Maybe switch them. Do you want to? Should we try that? Yeah. Everyone's like, "What are we looking at here?" Yeah, that's good to see. It looks great in front of me if you're online.
I see.
I salute the guy who had the confidence to stand up.
Yes, thank you. Thank you.
You're presenting something.
Although
Good to figure out for you, for however you want to do it.
yeah, definitely. I wonder if we could just mirror this really quickly.
Oh, sure, yeah.
Let's do that.
It's time for dad jokes when we have a break in the action here. But I feel like I'm going to use one I've already used. I got to come up with a new one. If anyone's got one, go for it. We're just doing a mirroring of the screens here to make sure that folks in person can also see what we're doing.
Here
online.
we go. Mirror
And
display.
Ronnie is on the ball. I didn't realize he'd get into tech support too.
Okay, I think that that does it. Looks like.
Yeah.
Let me just maximize this.
Sure.
Go away.
Hide that. Okay.
Yeah. Okay.
Awesome. Looks great. So we do have a code of conduct, and we ask basically that everyone be nice to everyone. And if you have any observing any behavior that is not in line with the code of conduct, please do reach out to Janet, Tommy, or myself, and we will deal with it. We also have a diversity statement. We just ask that anyone, we really want to reflect our community, and we ask that if you hold us to this goal of making sure that we have a diverse group of speakers, and encourage everyone to consider speaking at Data Science DC events. We do have a meetup in the works for October. Details coming on that soon, so check out the meetup page or get a message from us about it. There's our link. Encourage you to subscribe to our YouTube channel. We do post our meetup videos on YouTube whenever possible, so check that out for past meetups. Those are all of Data Community DC meetups are on that channel. And encourage you to join us on Slack. We have a DSDC-members channel that you can join. I'll put a link to that in the chat here in a bit. Community announcements. Does anyone have any event they would like to give a shout out for?
Sure. So first of all, Adam from Red Hat.
Bring Adam right over.
See it here. So on October 5th in Roslyn at the Convene Convention Center, we're hosting an event called Dev Nation Federal. It's kind of the 7th year running, minus, I think that's inclusive of the years of COVID where we were purely online, but this is back in person. So we're actually going to have a speaker on ethical AI. We've got some folks from C3 AI who are going to be speaking. We've got one of our guys is going to be talking about quantum computing and sort of how you can sort of start using quantum computing today, like leveraging IBM's quantum computers via some services that they have, as well as some breakout labs and workshops. So we're gonna have some hands-on implementations of AI ML for, I think we're doing fraud recognition as well, or detecting fraud, as well as maybe license plate recognition or an object recognition type of lab. And those are 90 minutes. I will get the registration link out to you guys. Maybe you could email that out. That would be cool. Okay. All right, cool. That would be great. And then I think the other thing is like we're really excited to be sponsoring, kind of hosting you guys here. We're happy to do it until you get back to, I remember the days I was telling them of 125 plus people at these meetups. So at that point, we're gonna have to change. But Red Hat just launched. So we're known for the operating system, Red Hat Enterprise Linux. We also have our Kubernetes platform called OpenShift, and we just launched OpenShift Data Science. So it's a full supported stack of data science tools that you can use on top of OpenShift. So pre-containerized that you can sort of leverage in a Kubernetes environment. So if you have questions about that, feel free to reach out to me, and I will stop with the commercial presentation now.
Awesome. Thanks. Thank you, Adam. Thanks for folks here. We know we are mirroring the screen, and we are going to adjust that right now. Thanks for the heads up. And also thanks, shout out to Bill with the dad joke here, in case anyone else missed it. When does a joke become a dad joke? When it's apparent. Yeah, got it. Good stuff. Good stuff.
Any improvement there? Oh, it's on this screen.
Still here. Yeah, still seeing both.
Yeah.
Thought we had it all. So we're showing a couple different places here, so it's a little tricky. Well, we think we might try something else next time. We might give it another shot. You're fine. I can just look at that.
Oh, there we go. Just want to find the. Let's try this again.
Yeah, that looks good.
Any luck here?
How's that looking there?
It's blackness.
It's black.
Infinite blackness.
William, the recording will be posted to YouTube, so subscribe to our YouTube channel. It's just the Data Community DC YouTube. So if you, we'll put a link to it in chat here in a minute, or just Google that and that looks good up there. That looks good on here. There.
Yeah. I wonder if I can just enter full screen. That would maybe close enough. I don't know.
Yeah, we just see those over there, but it looks good other than that.
Okay. I don't know. Maybe I'll just roll with that.
Sorry, Ronnie, put you on the.
No, it's okay. Okay. Yeah.
Cool. All right. So community announcements. Anyone else have community announcements you want to share in the chat? Go for that. Anyone else have community announcements here where we are? Yeah, Tommy.
Hi, everyone.
You want to do it up here and then?
Yeah,
All right.
Guess there's a microphone up here.
Yeah.
All right. So hi, everyone. Tommy Jones. In addition to being an organizer for Data Science DC, I'm also the president of Data Community DC. I just want to let you guys know that we have new bylaws coming into effect on January 1st that will allow everyone here to become an actual member of the nonprofit if you want. Details are still being worked out, but it would be for a nominal fee, maybe $10 or $20 a year to start, and you'd be able to elect the folks that would be on our board of directors. So give you a chance to participate in the governance of the organization. So I just wanted to let everyone know that that opportunity is coming up, and watch this space. You'll hear more about it.
Any other announcements, questions, comments? If we click home, it'll hide the ribbon. That's what I'm told here. I'll let you do that. If you don't.
All right. If I click
Home.
home.
See home.
I don't see home,
All
but thanks for the.
Awesome.
Yeah.
I
don't have anything too small, so I think it'll
awesome.
be okay.
Well, that's all I have. So it's now straight on to you, Ronnie. So thank you, Ronnie.
Yeah, thanks. I appreciate that. All right, let me move this out of the way. How's that? Okay. Yeah, thanks for having me. Before we begin, so I can kind of tailor the set list, so to speak, can you raise your hand if you've done any of this before or heard of it, maybe? Okay. And how many of you have done something of like, or tinkered with it? 3-ish, 4-ish. Okay, 3.5. Okay. So I'm hoping after this, you'll have sort of a foundational understanding of how this works, so you can go out and explore more, because it's a huge topic and there's no way we could, comprehensively cover it. I think this is a useful way to kind of, problem. Okay, useful way to kind of frame things and start it off. Back in 2020, there was this active discussion about whether vitamin D was associated with severity of COVID symptoms. Some people thought, if you megadose on vitamin D, you might have a lower risk of getting severe COVID symptoms if you got COVID. And if we think about this as sort of a philosophical exercise, what's the best way to determine if that's true or not? If we had all the tools at our disposal and we could change time and reality and sort of really see, I think what you would do is something like this. You would take someone like Mary and you would sort of timestamp it at a certain point. You would notice that in early 2020, she takes lots of vitamin D at high doses. You would continue following her forward. You see that she lives her life. She goes out with friends. She, does her job, gets a new job, etc. All these life changes. And then in mid-2020, she gets COVID with mild symptoms. But this information alone isn't enough to tell you whether it's because of the vitamin D, right? It could be her other aspects of her personality and being, right? So if we had everything at our disposal and we wanted to find this out, I think what you would do is something like take an alternative reality of her and copy her and hold everything constant, except in early 2020, she does not take vitamin D, but everything else is the same. She sees friends, she has a job she goes to, she gets a new job, drinks the same amount of coffee, everything's the same. And you would follow her forward in time. And you might see, I don't know, maybe she gets severe COVID symptoms, maybe she doesn't. But at any rate, the changing of this one thing while holding everything else constant is the magic, right? That kind of determines whether it was the vitamin D or something else. Obviously, we can't do that. That's just a made up example. But the closest thing we have to this are these things called experiments or A/B tests or randomized controlled trials. And the way they work, as I'm sure many of you know, is you just take a chunk of people, sort them into a treatment group and a control group. You assign some treatment, maybe high dose vitamin D, to the treatment group. You don't give anything to the control group, and you follow these people forward in time and see what happens. And you count how many would get severe COVID symptoms, and you sort of make this comparison between the two groups. That's probably the best thing we currently have to determine whether there's an effect. But there's a problem with experiments, that is, they won't always be applicable or doable. Sometimes they're not ethical, like in a prior life, I was doing lead research. I can't assign a whole neighborhood to get lead exposure and another neighborhood not to, and see how the children develop. That's wildly unethical, right? Other times it might be ethical, but it's not feasible. It's like very challenging logistically. So there's a big conversation in sociology and anthropology worlds as to whether equity and neighborhood income is related to violent crime in those neighborhoods, right? Some people think if it's more equal, there will be less violent crime. It's an interesting theory, but I can't do an experiment easily to test that. I can't assign families to move to different neighborhoods and sort of say in neighborhood A, it's relatively equal, neighborhood B, it's not. So it's tough, right? So what do you do? These are important questions and we want to answer them. So what I'm talking about today is this concept of causal inference. Causal inference kind of sits between proper, strong random experiments, randomized experiments, and simply looking at correlations. On one end, randomized experiments are tricky, but you can make really clear, strong causal claims as to whether something works, right? That's why they're so awesome. But on the other end, anyone can whip up a data set and look at correlations and say, I think there's something here. But the causal claims you can make with that are weaker. And I'll get into that in a little bit. And so I think causal inference is very useful because it bridges this, right? in situations where you can't do experiments, it allows you to, with some clever theories, take data you have at hand and sort of simulate an experiment in a sense, which is a really powerful thing. You can answer a lot of questions that way. So I'm guessing a lot of the folks here already have a good sense of what machine learning is, and you sort of, maybe you've used this before. And so I think it's useful to sort of compare what causal inference is versus machine learning, because there is a difference. They're related, but they're not exactly a one-to-one same thing. In causal inference, we can answer questions like, how does improving neighborhood income inequality reduce crime rate? Or how does increasing or decreasing the price of a product impact demand? What would be the impact if, you know, we enacted some federal policy where we reduce the average amount of sugar people would intake on a daily basis? This is not quite the same thing as a machine learning question, which is, you know, things like, I have a data set, can I cluster the neighborhoods and see there's a story there? Or, you know, I have a data set of users in the world, and I want to see which of them will become leads, or which will become customers, or who's going to drop out, right? Or I want to classify a set of like Twitter text into like low sentiment versus high sentiment. So the difference here is, you know, with machine learning, you're predicting something. You could be doing something supervised, unsupervised. With causal inference, like with an experiment, you typically have a treatment and you have an outcome, and you want to see like, what is the nature of that relationship holding other things constant, like in an experiment, right? Like in the case of COVID and vitamin D. If I hold everything else constant and I vary vitamin D, does that actually have an impact on people? Those are the kind of things that causal inference answers. So think of causal inference as closer to experiments than to standard machine learning in a sense. Yep.
Question from Rajiv here in chat. Is the extreme case of causal inference logical inference?
I'm not familiar with that language, but maybe. I don't know. I have to look into it. Yeah, I don't know. Thing about causal inference is it's used in a lot of different fields like econometrics, epidemiology, psychology, and they all have different names for the same thing. And so I don't, maybe, yeah, I don't know. But I'll look into that. Okay, so I want to be mindful of the time here. You know, there's a lot of ways you can do causal inference. You can use advanced models, you can use graphs like this. I think a good starting point for us is to frame it as a graph problem and kind of go from there. And so some of you may be familiar with what a graph is. If you're not, I'll just quickly explain. Each of these circles with letters represents a concept, or like it's sometimes called node. And the arrows represent a causal relationship. So this is what this is saying is that A causes E. Doesn't matter what A and E are, they're just some concept, you know, could be happiness, could be the engine of a car working, doesn't matter. B causes E, B causes D, which in turn causes E. And then sometimes what you'll see on the bottom between C and D is this bidirectional, which just means either we don't know or it's just a correlation, but it's not necessarily causing anything. So it's helpful to know how to interpret this for the next step. All right. So this is what a causal graph is. It describes the relationships between ideas, whatever they are. Right. So we're going to take this concept of a graph and we're now going to, I want to introduce 3 really important types of relationships that you'll have to know about if you want to do causal inference. Right. The first one is something called confounding. It sounds like you're familiar with this, maybe. Okay. It's called confounding. Now, I'm going to go through these 3, but remember, there's always a treatment and an outcome, right? We want to estimate the effect of a treatment on the outcome. For these 3 causal relationships I'm going to show you, the first of which is confounding, as much as possible, you want to eliminate confounding. Confounding is a bad thing. The other 2, you don't really want to eliminate. Okay, so first one, bad, we're going to try to like find it and kill it. Next 2, we don't really care as much. It's interesting to identify them, but it's not critical. to control for them or, get rid of them. So what's confounding, right? You have a treatment and an outcome. Confounding is a third variable that is causally related to both. And this is going to be super abstract, but I'm going to go into a specific. But that's what a confounder is. It's a bad thing. It prevents us from accurate or assessing well the relationship between treatment and outcome. Really classic example is if I want to see the relationship between coffee consumption and lung cancer, it's well known in the epidemiology field that you're going to find an association. It's completely bogus. It's completely bogus. There is no biological reason that coffee consumption would cause cancer in any way, like liver, skin, whatever, lung. The problem is, this is actually true. There is a causal relationship between smoking and coffee consumption. It's not just a correlation, actually. In the literature, there is a causal relationship. It's psychological and it's a real thing people have studied. And there is a causal relationship between smoking and lung cancer. And so as a result, smoking is confounding this relationship and making an association between coffee and lung cancer appear to be there when it's not. It's fake. And so that's why confounding is a really bad thing, right? It induces these spurious relationships between coffee and lung cancer. If you had a data set from the CDC of like 1 million people and what are their daily coffee consumption patterns and how many of them have lung cancer in some time period, if I just do a simple dumb correlation, you will find it, unless you control for smoking status, and hopefully it's in that data set. It's a confounder. So you always want to control for these. I can't really tell you what direction it will induce that fake relationship in. Sometimes it will make a positive relationship appear between the treatment and outcome. Sometimes it will reduce it. It depends on the context. What we call a scenario where you haven't appropriately controlled for smoking, this confounder here, is something called residual confounding. In practice, it's almost impossible to fully get rid of confounding, but you want to do as much as you can. Yeah, we can skip that. So here's another example. If you were the mayor of a big city in this country, and there was a violent crime problem, this is another kind of canonical example, and you had a massive data set, you were like an analyst for the city or something, and the mayor says, can you do some data mining on this and tell me what's related to violent crime? You will almost certainly find a correlation between ice cream sales and violent crime. But does that mean you should stop ice cream sales in your city? Probably not. That would be stupid, right? What's actually going on here is hot weather is again inducing a confounding relationship between these, a confounded relationship between ice cream sales and violent crime. And that's because hot weather causes ice cream sales and hot weather causes violent crime. That's just a fact. It's in the literature. And so if we can find a way, which we will a little bit later, to control for hot weather, the fake relationship between ice cream sales and violent crime goes away. So you don't have to tell your boss, the mayor of the city, that there is one. Okay, so I think hopefully I made it clear why confounding is a bad thing. You want to get rid of it, right? The next causal, yeah. Yeah. Thank you. Yeah. Question was, how do you control for confounding in practice, mathematically or just otherwise? There's a number of ways you can do it. We're going to go through a modeling exercise later on in this talk where we do that. But there's like one of like 6 ways to skin the cat. You can, maybe the most basic way and probably like among the worst ways is, let's say hot weather is a 1 or 0 in this data set. Like imagine it's a 3-column data set, right? If I only look at the zeros where hot weather is 0, I've broken confounding because I've forced 0 variability on that variable and it no longer exerts an effect. It doesn't matter if it's a 1 or a 0. As long as I make hot weather a constant, there's no variability. And in that subpopulation, there's no longer confounding. I mean, that's kind of a dumb way to do it though, because you'd like throw away observations, but there are better modeling ways to do it. And we'll get into that. Okay, second causal relationship that you don't want to control for is something called a collider. And the way that works is it's the opposite direction. Treatment causes something, outcome causes that same thing. It's sort of a shared effect between treatment and outcome. An example of this is if you're looking at the relationship between smoking and lung cancer. If I look at my data set and there's a column there for number of sick days taken, I'm like, oh, cool, let's control for that. It's in there, might as well. I will bias the association between smoking and lung cancer. That's just a mathematical fact. You can simulate that yourself, actually. You can make up your own data and force a collider to be there and control for it, and you will see that it changes the relationship in a way. So I guess maybe at this point you might be wondering, well, how do I tell if something's confounding or a collider, right? Two ways. One, you have to sort of look at the data yourself and see what the naive correlations are between these different nodes. Two is you have to have domain knowledge, and there's just no way around that. Unlike some parts of machine learning where I have my thing I want to predict, I have the outcome, and I have 100 variables, and I can just throw it in and make a good prediction. You can't do that here. You have to think through the context of it and have that domain knowledge, unfortunately, or I won't say unfortunately, you just have to. And so, yeah, you never want to control for a collider, and I'll get into later on how to control for things, but just remember that. Okay, last thing is something called a mediator, which is just, there's still a third thing there, but now it's sort of like they're chained together, right? Like one thing causes the other, which causes the next thing. If I control for that mediator, any relationship between these two things vanishes. Does that make sense? Because the critical pathway getting there is gone now. And so if I'm looking at, again, smoking and lung cancer, and I don't know how you would have this, but let's say you magically have like a data on microscopic lung cancer damage in these people, like where you can like see like clinical signs of that lung is damaged before cancer. If I control for that, then there's going to be there'll be a very low association between smoking and lung cancer, when there really should be a big one, because we all know smoking causes lung cancer. So just to sum it up, control for confounders, try to find them, try to eliminate them. We'll get into that. Do not control for colliders, do not control for mediators. You don't want to touch those. You want to know what they are in your data set if they are, but don't control for them. Okay, and this is kind of a controversial point, but I got to make it. Standard variable importance metrics do not tell you anything about the causality in those variables. I think they're useful. They're useful for sort of understanding the complexity of your model, understanding if I looked at 100 variables, but actually only 6 of them have any signal or like predictive power in them, so I can pare down the model and make it simpler. But in the example of the ice cream and violent crime in a city, if I had a data set of 100 variables and I throw them into the model, and ice cream is one of them, any standard variable importance method will show that ice cream is very important. So use them if you want to sort of get a sense for like what's predictive of what, but please don't ever interpret them causally, which is super controversial. I had someone like almost fight me about that like 6 months ago or something. That was a big point. Okay. All right. So causal inference is not magical, though. You can't just apply it in any scenario. There are assumptions you have to follow. They have kind of fancy names from like the academic world, but they're really simple. So the first one is temporality, which means if I'm going to understand the relationship between this and this has to occur in time before this. It would be meaningless if I put in like lung cancer here and smoking here, because the causality is reversed, like one comes before the other, right? And so it's important that you maintain that in your causal inference analysis. The next one is called the stable unit treatment value assumption, which just means if every row, in the example of like a data set where each row corresponds to an individual, no individual can affect the outcome of any others. They're all independent. I think that's pretty standard assumption, like I think in most modeling scenarios, but it's important, right? So I can't just use this on social network data because people talk to each other and they impact each other, right? So it doesn't quite work in that domain, although there are more complex ways to make it work, but I'm not going to cover that today. Okay, and then positivity, which is a fancy way of saying you have to have enough data and enough variability in your data in order to make these models. So think of it this way. I have a binary treatment variable and a binary outcome, right? And I have 1,000 observations. In that 1,000 observations with just those two variables, I have to have enough instances of 0 treatment people getting the outcome and not getting the outcome, and the opposite, right? If I add in more and more covariates and variables within each of the strata of those, as I kind of thin the data set and get more and more strata of like no treatment, high age, lives in the zip code, and that there has to be enough instances of outcomes being both. Otherwise, the model's not going to be able to learn what's actually going on. And this is violated a lot when people, take 1,000 observations and do causal inference with like 100 variables, because there's no way the model's going to know within each of these substrata what the relationship is between treatment and outcome. It's just not possible. Then the last one, which really can be tough, is that you have to have included all important confounding variables in your analysis, and sometimes you just won't have access to them, and it sucks. But in some scenarios, you just have to kind of throw in the towel and say, like, I can't do this meaningfully because I want to see the relationship between some treatment and some outcome, and I only have one kind of so-so covariate to control on. It's not good enough, and you wouldn't want to share that with anyone else. The result, it's not trustworthy. Okay, so I'll try to wrap this up in like the next 10 minutes so there's time for questions. But so now we're going to get to the modeling piece that someone asked about before. There is a method that I really like. It has a really pretentious name. I don't like the name, but I like the approach. And in fact, this is called different things in different fields. Like in econometrics, they call this S-learner. I don't like that either, but it's a really simple approach where what you do is this. Let's say, I'm just going to present like a simple table, right? Because I think that's clear. You have a treatment and you have some outcome, right? On the two far right columns. I want to see the relationship between them, the causal relationship between them, as if I were doing an experiment to see, what the relationship is. Let's say I've already identified the confounders and I put them in here. That's covariate 1 and 2. So I know they're in here and I want to control for them somehow. I want to like remove their effect on this treatment outcome thing. But that's all they are. There's no mediator in there. There's no collider in there. It's just those two confounders, covariate 1 and 2, right? What G computation is train a model to predict all of these variables, the known confounders, covariate 1 and 2, and treatment to predict the outcome. You can do that with sklearn, doesn't really matter. The only thing you want to watch for is you want the model to be relatively balanced and, have good metrics. And then once I have a trained model, what I do is I take my data set, I copy it, and I force everything in the treatment column to be a 1, while holding constant everything in the covariate columns, right? And then I make new predictions using that trained model. And I might find that, okay, well, I see some different results here. The results on the right there kind of look like this now. I hold those, I save them, and now I force everyone to have a 0 in the treatment category, holding everything else constant, and I make predictions on that. And so now you see on the right here, I have predicted outcome in the treatment group, predicted outcome in the non-treatment group, side by side. you simply subtract them like this, right? So like 22.5 minus 18.5 is 4. I do this for every row, every observation, and then I average it at the end. And then this is what they call the conditional average treatment effect, which is a fancy way of saying like the effect of treatment on the outcome controlled for those two covariates, those two confounders. Does that make sense? Yeah. Okay, now that's a good question, because that kind of gets at the positivity assumption. If I'm using a lot of continuous variables, you're going to get in a situation where the strata that you're sort of concerned with are like increasingly small, and it gets tricky. And so ideally, you would want the covariates and the treatment to be binary, which, I mean, it's not, you don't have to do that necessarily. Like I self-plug here, like I have a Python package which handles continuous treatment variables, but it complicates things. Yeah. Yeah. Okay. Does that make sense to everyone else though? Or yeah.
Why does it work?
Why does it work?
Yeah.
Best intuition I have for this is kind of like in the beginning where I was talking about the COVID example and vitamin D. If I had an awesome predictive model that controlled for, let's say that it controls for all the confounding and it really captures like the world and how it works, I could at the start just say, take Mary, these are her covariates, force her to get the treatment. And then take the alternative universe where I force everything to be constant and make a prediction where it's 0. And if it's a good model, if it predicts well, then that's sort of, that'll give you the answer. So it's kind of philosophical in a sense, like causal inferences, you could look at it this way. It's not just like simulating an experiment, but also predicting scenarios where you do and don't have some treatment well, predicting well, I guess, if that makes sense. Okay. Okay, so to kind of close with, I thought, I mean, I bet some of you might try this afterwards. So I wanted to present like a simple flow chart to kind of explain where to go or how to do it. So let's say this treatment you want to explore is, could be binary, could be nominal, could be ordinal, could be continuous, right? If it's binary, it's really simple, actually. You just use something simple like sklearn and do what I showed you up here, where this treatment was 1 or 0. That's all. The outcome can be continuous. It can be binary. Doesn't really matter. If it's continuous, do what I showed you above in the few slides. Just get that average effect for treatment 1, treatment 0, and subtract it. If it's binary itself, it's not that hard. What you can do is something like calculate the average probability of outcome equal 1 in this group, and then the average probability of outcome equal 1 for no treatment. And then subtracting those two, you get the causal difference, which is just, it's on the scale of probability. So it could just be, you know, outcome is 5% more likely with treatment or something like that. Or you could calculate a causal ratio at a relative scale, which is just P1 divided by P2. And you could say likelihood of the outcome is twice as high if I do the treatment. And yeah, it's the same sort of thing, just different scale. If your treatment is continuous, another shameless pitch here, there's a package called causal-curve out there, and it is meant to handle just that case. So price changes, levels of lead exposure, like sort of just the sort of continuous range of it, where you don't want to make it straight like binary. You can sort of see, you can visualize the causal curve, like as you move up and down the treatment values. So that's all it is. And then if the outcome is continuous, there's an approach for that. If it's binary, there's an approach for that too. It's meant to sort of mimic the sklearn API. So it's very familiar, like fit and, you know, that sort of thing. So that's it. Any questions or anything? Yeah.
before we actually do this process. Right?
Yeah.
Do you have any recommendation about control?
Oh, sorry. I should say, doing this process is controlling the confounding.
Oh, so
Yeah.
the variance can be the confounding variable.
Yes, that you only want them to be confounders that you know of. You throw them into this, make the predictive model. It takes these three things to predict this. And the act of doing this exercise controls for those confounding variables.
In general, if you have a confounding variable, when that's the variable, you actually introduce like linearity, like so you don't care about.
Sorry, what's that?
Kind of linear with each other.
Yeah, I mean, oh, sorry, what's that? Oh, yeah, sure. So I think you were asking what to do if there's collinearity, like between. Yeah, I mean, I would say all the confounders I've ever seen are sort of, there's partial correlations with treatment. If it really is like a one-to-one sort of mapping between the two, then yeah, unfortunately, there's like nothing in the world that will help in that scenario. But thankfully, I think most of the time it's not like that. It's like, you know, even I don't know, trying to think of an example here, like ice cream sales in summer. As obvious as that might seem to be, like a, yeah, that's a one-to-one correlation. It's still going to be, you know, like a moderate correlation or something. So there's room. Yeah. Just make sure these aren't colliders and mediators. That's all. My final warning. Yeah.
There's a good discussion people are having.
Oh yeah, sure.
People are having a good discussion here in the chat. I'll let you like maybe
Oh,
scroll if you want. They're kind of answering their own questions there. And also, which is great. But try to maybe just pull out that one person had a question on how do we find these confounding variables? Like how do you start to identify them in your experiments? Like how do you, it's kind of gets domain
sure.
knowledge, right? But
Yeah,
okay.
totally. Yeah, you have to have domain knowledge. You're not going to be able to find confounders if you have zero domain knowledge. Because interesting fact. I mean, if you like change the direction of these variables and all you have are these three variables and all you can do is look at the pairwise correlations, how do you figure out if that's confounding or mediation? Or you can't. I just have to know, medically speaking or whatever, that smoking causes this, and based on evidence and experience, and that in turn causes lung cancer. So you have to do that, and you have to verify that in this case here, you know, we have that domain knowledge. We know there's a connection here, but actually in your data set, is there a pairwise correlation between these? I think there will be. I think it'll be moderate, but sometimes by fluke or whatever, it's just very weak or there is none. And if that's the case, empirically speaking, in the real world, there cannot be confounding here actually. So confounding has to be, is there a pairwise correlation between these things? Like, do you actually see these in your data set? And then also, do you have, through your domain knowledge, an understanding that these things cause each other? So those are the two conditions. Yeah. Let's see.
Read that.
Yeah. If you randomize everything, you won't have confounding. Yep, that is true. I mean, that's the magic of experiments. By randomizing people into A group and B group, treatment and control group, you've broken confounding because, yeah, you've basically taken out one of these arrows. And so there's no longer any confounding, which is great. Yeah.
I have a question. So
Yes.
Say like from common sense, we know that like carbon will cause related to more ice cream sales. How about in the data? So in the data, we might see only like 0 and 1. So how do we know the direction of the arrows?
Yeah. How do you tell the direction of the arrows from data?
Yeah.
So the thing is, like with data alone, you can't actually, because there could be a positive correlation. There could be, well, I guess you can rule out, you can say definitively there is no association in the data, that there's a zero correlation between them. If I do like a Pearson correlation coefficient, if it's 0, there just isn't a correlation. But it could be a positive correlation. It could be a negative correlation. This arrow doesn't mean anything about the direction of the correlation. It means this causes something. So in another world, hot weather could reduce ice cream sales, or it could, in another universe, increase ice cream sales. The data itself won't tell you the direction of the arrow, if that makes sense. Like they're two different things. That's probably not a great example. Let me think of a different one for you.
Maybe going back to your causal graph, if you have multiple directions, that might be a little.
Yeah. Let's think about this. Okay. I mean, if you were totally new to the universe, you didn't know anything about people and aging, you might see a relationship between having white hair in a hospital and your likelihood of good outcomes in the hospital, right? Like, I think if people tend to have white hair, they're probably, I mean, knock on wood, this doesn't happen, right? But like, you're probably going to have worse off outcomes because you're older and you're more frail, right? Not knowing that domain knowledge at all, and not knowing anything about aging and white hair, like if I just had a data set, there could be a positive or negative relationship between the presence of white hair and outcomes, right? But I wouldn't know what causes what. Does that make sense?
So the process, what process, what we know by
Domain knowledge, exactly. Yeah. Oh, here's a warning. There are methods out there that say, give me the data set and I will determine the arrows and the direction of the arrows. They call it structure learning. Please don't ever use that. I don't trust it at all. I think it's a WMD, honestly, it's not good. Yeah. I mean, I've played around with them and I've tried, like, you can get these data sets, which are like gold standard truth data sets where they know ahead of time, you know what the directions of the arrows are and the sort of strength of them. There are data sets like this out there. And you can try 5 different approaches for structure learning on them, and each one will give you a totally different result. I don't know. I mean, I hope no one in the audience is building these things. I think they're garbage, honestly.
It's such a big area, and then we have some people who've had some experience here, which is great. I'm going to maybe just jump to one thing here that I think is kind of interesting. Doug said, you can have causation without correlation if the relationship is nonlinear. For example, food consumption is positively associated with health until you eat too much, so you go up and then like you. Is that it?
Yeah. So I guess like my definition of correlation was a little too simple there. Like maybe putting aside like a sort of simple linear Pearson correlation or something like that. I mean, the ability to see like a relationship, a pairwise relationship between two things. Like there are correlation coefficients which capture nonlinearity, and like you would see that in these pairwise things. But yeah, you're totally right. Like it's like a well-known thing that if data looks like this, like an X and a Y, that's like 0 correlation. The line just goes right through that. So yeah, you're right. Like right. But there will be a relationship between them.
Yeah. Absolutely. I see other people are asking me questions here too. People are sharing some great recommendations here in the chat too, so check those out. Pip install causal data is what Stas says. Yeah, there's a number of packages I know in Python and R, I think, around causal inference. And do you have some?
There's a great one called Causal Ml, which actually implements this. They call it S-learning, but it's implemented, so it's ready to go. You don't have to do this yourself, although this is just like 20 lines of code or something. It's really easy. Causal ML. I believe it's Python, but there may be an R one too named that. I'm not sure. Yeah.
A lot of times you see someone who it's in R or Python and someone says, that's a good idea. Let's take that over here too, right? Yeah, awesome. All right. Other questions here from anyone in the audience?
Yes.
So like in trying to you see some factor and you decline the application Friday. Can you keep application of your past compliance reviewed by the government?
Oh, interesting.
Question?
Okay, so I think the question, let me know if I'm off base here. I think your question was like, can you use this approach to almost like make models more explainable or something? Or like,
supporting this financial, right? Which is why people-
Ah,
It's all the-
yeah,
Same number, like,
um,
you keep-
yeah, I hear what you're saying.
So getting at like regulatory, would this pass muster with financial groups that require financial, some countries in the United States in particular have to explain
Yeah.
why someone didn't get a loan if they deny a loan to them, so.
Yeah. I tend to think of explainable ML as sort of being a different category, maybe. And one thing to keep in mind is people use this stuff, like there are whole teams in big tech, like Netflix has an entire team which just does this. But at the end of the day, causal inference is still going back to the top up here. It's still an imperfect approach. It's not as good as an experiment. So I guess I would take the results of these with like a healthy portion of like skepticism,
I think to answer the question, like all good questions, the answer is it depends, right?
Yeah,
So
that's true.
certainly
Yeah,
it depends upon which variable you're making the decision. If you find some causal relationship
Yeah.
based on race, no, that's not going to pass government muster. right?
Yeah.
Even though your
Yeah.
model agrees with it, that's simply not going to pass regulatory control. You find something else that is, and there are laws about what you can and can't discriminate on. And so you got to figure that into as part of the domain.
yeah, that's great. All right.
Any other
Any other
questions?
questions? Explainable ML.
I'm
Nice.
sharing that, I like that book by Christopher Molnar, so a good one.
Oh, cool. Okay, nice.
Awesome. Well, thank you everyone for joining us. People are coming in here with questions quickly. Okay, well, we'll give it a minute. Is there an informative budget of how many graphs?
What things that they're sharing.
Yeah, that's a good idea.
Oh, sorry, what was that?
She's saying we could maybe share it to the screen. Oh, here.
Oh,
we can
yeah.
Chat here.
Yeah, right. That's
Ah,
okay.
try to put this off.
Is there an information budget of how many graphs you can test? Well, it's really hard because as the number of nodes increases, the number of possible graphs you can make is super exponential. It's worse than exponential. So it's a real big problem. Another reason not to trust structure learning, honestly. Those higher. I take clinical trials. Yeah. I mean, I'm not sorry. I didn't mean to say that like if an experiment shows something, that is the truth with a capital T going forward. I just meant if it's done well, the causal claims you can make are stronger. And so I might take the results of, I would say this, if I do 5 causal inference exercises on a topic and I find there's some relationship, to me, that has as much value as one well-run experiment, maybe, or something like that. And so I would rather invest in that, honestly, than just spend all day doing lots of causal inference exercises. But sometimes you don't have access to the experiment. And so it's a way to sort of partially get at the truth. Sorry, did I misunderstand something? I was thinking more of p-hacking.
I think maybe get the same idea, like just trying to find significance by running a whole bunch of.
Oh, yeah, for sure. It can be the problem sometimes where like oftentimes people will do this type of work to evaluate a program. Like, did this product work? And you can get a situation where, hey, we didn't find a great story with this. Can you try some other stuff? Like try some other confounders and just see what happens. And you do that 3 times and your likelihood of finding like a false positive result that is significant it goes way up. So eventually you will find a good story. It's going to be completely BS, but you'll find it. So it's not a good approach. Yeah.
Question about DAGs. Does it have to be a directed acyclic graph?
I mean, I think the standard approaches I've worked with kind of assume that, well, Yeah, I imagine like if you want to do some of the standard causal inference approaches, you sort of need that assumption. Otherwise, you get into like feedback loops and nonlinearity and all sorts of ickiness. So you probably want to avoid that. Yeah. Yeah. All right. Sometimes it seems like, oh, yeah, really fun. Really fun. Sometimes it seems like if you can randomize, the randomized experiments are easier. Yeah, totally. Yeah, they're really straightforward. At the end of the day, you're just doing like a t-test or something once you do an experiment. So yeah, it's really straightforward and you can make stronger claims. Oh my God, Dan Garmat.
Plant in the audience.
Yeah, it's a thanks, Dan. What are some cases the treatment is continuous, that the causal curve package works well? Yeah, so some examples are, what if the treatment is waiting time, like the number of minutes someone spends in a line? You know, what's the causal effect of reducing that? Price going up or down? Doses, exposure to something, like the dosage of it isn't necessarily binary, and you probably want to look at it that way. So yeah, and the tools I'm familiar with generally do actually require normality, which is, I know that's a problem, but yeah, it's just something to live with potentially. So thanks. Yeah. Okay. Yes, you okay, I just might jump to this next one. What are some of the biggest challenges in causal inference, especially in health and medicine? The ones that we've encountered, Dan and I, are not having the full set of relevant confounders. You know, we'll get a data set and we'll have a program that seems really awesome to test, and we'll have a whole suite of variables to look at to control for, but they're really complex mechanisms and the process is really complex, and we think that we're missing confounders. And you know, sometimes you might do this approach and you get a result that's a little bit nonsensical, and so you're like, this is biased somehow, I'm missing something, and you just have to kind of throw in the towel. Like, I can't test this any better. I don't have access to all the variables I need. So that's a big challenge. And I imagine, like, particularly in healthcare, where it's just, you know, it's a tough space to get the whole suite of data on things on. Oh yeah, tell me if I should stop.
Yeah, I think maybe take this last
Okay.
question here from Matt about where they've worked on e-values to assess sensitivity to unobserved confounders.
I haven't. I'm gonna have to check that out. I wonder if that's like in. So I come from the epidemiology field, and maybe that's from another field, and I'm just like not familiar with it. But it sounds interesting. Be curious, yeah.
Cool. All right. Well, thank you everyone for your questions, and thank you for coming tonight. Very lively discussion. So special big thank you to Roni for
Thank you.
excellent, y'all, and we'll get this up on Meetup.
All right.
Or on YouTube. See ya.
Take it easy.